So thanks very much for inviting me to tell you a little bit here about the Cambrian explosion of cryptographic proofs. I'd like to ask how many here have attended the Starkware sessions 2 weeks ago? Because I'll use some stuff from there. Okay, not too bad. So I'm scheduled to give 2 talks, one after the other. This one will be more fluffy and blockchain oriented, and the next one will be a little bit more mathy. And before I give somewhat of a survey of the world of cryptographic proofs within blockchain, I'll just start by giving a little bit background on myself and also a lot okay, so my journey, and I think it's also part of the greater journey of cryptography of zero-knowledge proofs within blockchain. So, because I think I've been there from the start of this particular journey of the merging of, or the usage of proofs inside blockchains. So, I know you can't really see anything but for this thing. Integrity was beautifully defined by the author C.S. Lewis as doing the right thing even when no one is watching. And what all of these cryptographic proofs, the snarks and the starks and the plonks and the bulletproofs and the myriad of other things, they're all means to an end. And the end is integrity. It is to know that the right thing was done even when you're not watching. And so that's the goal. That's what we achieve. And the particular way in which it is achieved was already beautifully, I think, for me, the starting point is this amazing paper from 1992 that came. So in the late 80s and early 90s, there was this I tweeted that I'll be giving this talk, and someone said that there was a Cambrian explosion of Cambrian explosions. So in the late 80s, I'll add to that. In the late 80s and 90s, there was a Cambrian explosion of works that understood interactive proofs, starting with the 1985 paper by Goldwasser, Mikali, and Rakov, and then leading on to like a flurry of works on PCPs and IPs and MIPs. And of course, this line of theoretical works has been, this tree that keeps on giving fruit till this very day. Things like MIP star equals RE, and amazing constructions of quantum LDPC codes and linear LTC codes, for those who heard. So this is a field worthy of continued study. But already back in those days, there was this amazing paper by Levin, Fortnow, and Segedi. And here's just one beautiful quote from it that basically epitomizes all that we're doing today at Starkware and these other places. It's all about this. So they said, in this setting, this is from 1992, a single reliable PC could monitor the operation of a herd of supercomputers with powerful but unreliable software and untested hardware. And I just want to give a little bit of a flavor of how they implemented it back in the day and what has changed. So let's take it into a very concrete blockchain setting. Here's an example of a statement that you may want to have proved, or you may worry about its integrity. Someone is claiming that she started with a state of accounts whose hash is X, processed 1 million transactions using a specified program that we all recognize as a good program, P, and reached the state hash of Y. And we would like to know that the right thing was done even when we're not watching. And the right thing is really specified by P, okay? So what the tools that were invented already in the 1990s showed was that there's a way to take this statement, and in fact any statement in non-deterministic exponential time, which is the beefed up version of NP that you may know of. So you can take any such statement and convert it into a Sudoku-like or Sudoku. I don't know how to pronounce that word exactly, but you know what I mean. So one of these puzzle things. And the exact size and pattern, the exact size is actually determined by by the number T of transactions, and the exact number patterns that are partially filled in and the kinds of constraints are determined by the program P and the inputs, okay? So there's a way to convert such a statement into this puzzle, and then a prover submits a solution, which is just the filling up of these entries, and a verifier then uses randomness, samples a very small number of entries. The verifier already knows what would be good or bad for this particular constraint that she picked, and then reads the entries, and based on this one sample decides whether to accept or reject the claim. And the magic, again, this was all known in the 1990s already, is that sampling constraints takes exponentially small time. So why is this important? The verifier need not open up this whole big table. The verifier can do everything extremely succinctly. The verifier is anyways going to sample just one constraint. And in fact, the verifier can sample this one constraint and all the information needed to verify it in time that is, polylogarithmic in the number T of transactions or the size of the computation, and polynomial in the program P that describes it. Okay, so that's succinctness. The other amazing thing is that, this is not so amazing, but this is called completeness, good proof. So if the statement is correct and the prover is honest, then there's an algorithm that will let him fill in the entries so that all constraints with probability 1, if you sample a constraint, you see that it is satisfied. The most amazing and also the most mathematically challenging aspect to understand is the soundness. And it says the following amazing fact, that if the statement is incorrect, then no matter how you will fill this table, at most 1% of the constraints will then be satisfied, which now leads you to a very simple polling method. You do one check, your error is 1%. You do 2 checks, your error is 1 in 10,000, and so on and so forth. So if you repeat this a very small number of times, you will know that the statement has been computed with integrity up to a very small error, which you could make, 2 to the minus 100 or so to your liking. And this thing is absolutely amazing because basically we get the essence of polling, right? Polling an election or polling some very large group. We get the same effect, but with respect to the integrity of a computation, of any computation. Now, I could say that my own work and the work of Starkware basically can be summarized as taking the PCP machinery and changing it to be somewhat interactive. So instead of having just the prover fill one table, there's actually an interactive process in which a first table is filled, then randomness is sent, and a new table is generated. It is filled, a new table is generated a number of times, and then there is these 3-dimensional constraints that are applied to all of them. But essentially, it looks very much like the old PCP from the 1992s, and it still gives you this effect that a single reliable PC, so that's the weak machine, that's the verifier that works in time that is polylogarithmic in the number of steps of the computation, can know whether the right thing was done even when it's not watching. So I could say that all of my the later part of my academic career and all of my entrepreneurial career was basically working very hard to chisel and remove just 2 letters from all of this, and that's the impractical. So the initial constructions were impractical. If you took the BFLS paper and you tried to implement it, and people have looked at it, for instance, Professor Miki Benol told me that he, and I think in the 90s or aughts, he looked with students like, what is the minimal size n for which you get something using these methods where it's more efficient to go through a proof than to just do the damn computation, and there weren't enough atoms in the solar system to write down such a proof. But over a very large number of works, I'm focusing here on my works, but of course there are many, many others. Basically, we made this slightly more practical. And now, all of this is about cryptography or complexity theory, but there's this other aspect, right? And we're talking here about blockchain and zero-knowledge proofs. And that's related to this single reliable PC. So, right, all of these proofs give you this ability of something that is very weak, but trusted, right? It's reliable, but it's very weak. It has the ability to check the integrity of something that is of much greater scale, but unreliable. So the question now is, where do we find such a setting where we would like to use this technology? And the nice thing is that, and this is some fluke of chance, that right around the years where quadratic span programs and linear PCPs and SNARKs and STARKs and many other, and bulletproofs and many other of these constructions were maturing, something completely different emerged, and that's of course blockchain. And I think that had there been no blockchains around, I know that the field of startups or companies that are working with ZKPs and trying to make products and systems out of them would have suffered much more. It would have been much harder to find use cases. And in fact, probably Don remembers this, but in the early, like in 2013, I actually went to Stanford to consult with him on the entrepreneurial aspects of like finding where to deploy proof systems. And I think we didn't look too much in blockchains. I think they were just, at least to me, they were like frightening and scary and so on. And I remember I remember many things from that conversation, but I'll just share one. We were discussing all kinds of things where, in like standard security of airlines, maybe you could use proof systems and things like that. And I think the interaction was, I was raising one idea after the other, and Dan was like, oh, you could do it this way, you could do it that way, this won't work, that won't work. Okay, so at some point I was like really frustrated, and this was right in the beginning of the journey, and I said, oh, but like now I'm completely depressed because what you're saying is like I asked him why. I mean, I might spend a whole year on this, and then it all goes down the drain, and like I don't know what good this is for. So Dan started laughing, and he said, "Oh, like what do you mean? If you spend 1 year on this and you fail after a year, this is like a huge success. Your problem is if you spend 10 years on it and then you fail." So and indeed, actually, the very first attempt I did fail after a year and a half. So not a year, but anyways. So where do we find this reliable PC? Where can we take this beautiful technology and apply it to? And the answer comes from blockchain. So the peer-to-peer nature, this thing where there's no single source of trust, leads you to something, that's blockchain, that is very reliable, but also from a computational point of view, it is very weak. And I'm sure everyone here knows that blockchains, each transaction is very costly to have it processed by the blockchain, which is, that's a result of these systems being very weak. And you could think of something like Ethereum. So Bitcoin is the most important, but it also is so computationally weak that it cannot support general computation. And Ethereum is the first to offer you the analog of a single reliable PC. It can do any computation, but it is very, very weak compared to what the cloud can offer. And now suddenly we have this single reliable PC that we really, really trust. And we have the technology that allows it to scale, because you could use the single reliable PC to monitor a herd of supercomputers or much greater computers that are working on the cloud, and you need no trust assumptions about those computers as long as you have your single reliable blockchain, which for us at Starkware happens to be Ethereum. But and to me, this realization came in 2013. I think I was the first to realize that general purpose proofs can help in the context of blockchain. And this was probably after exploring, as I mentioned, all these other routes that weren't as useful for it. And as a result of this, I found myself both being a part of Zcash, the zero cash paper, and Zcash cryptocurrency, which is the first general snark usage, ZK snark usage for privacy. Of course, there were specific non-general computation uses of ZK much before that. And in 2018, Starkware, we co-founded it, and it's the first to deploy general cryptographic proofs for scalability over blockchain. Okay, so this is just a bit of background on my story. And now I want to talk about the Cambrian explosion of cryptographic proofs. So I first gave a version of this talk in November 2019, and I said, oh, look, there's so many proof systems. And then I gave 2 months later, like 2 months later, I was giving the same talk, and as you can see, like I updated, I said, wow, by now there are like many, many more. Now this was 2019, and when I was working towards this talk, so I realized that it's like completely impossible to do justice to the amount of research and constructions in this area. So Dan had 3 points, 3 dots for all the other proof systems that he didn't mention. So I'm not mentioning anything that happened after 2019. And if your favorite proof system isn't in it, so it's not in the 3 dots, it's somewhere in the awesome new stuff. And there's a lot of research going on, and frankly, I can't even, it would take me a very long time to know all that's going on and do it justice. So I apologize, I'm not going to survey and tell you everything that is to be known about the landscape of cryptographic proof systems. But this is this school is about blockchain. So I did like ask around. I used Twitter a little bit, and I also from asking a few folks around, I did ask various teams that are deploying or soon to deploy blockchain projects on blockchain. I asked them, okay, what proof systems do you say that you're using? And roughly I got these answers. It's slightly more involved because there are things that are, a lot of teams talk about being plonkish, and they mean various variants that in improvements over plonk, things like plonky, plonky2, f-flonk, and p-lookup, and so on. But so this isn't a correct picture, but it does seem that there are like a few classes of proof systems that are used, and in my survey I'll try to focus a bit on them. Now, so who thinks that more systems deployed on blockchain, so here's a poll for you, like what is it more about, privacy or scalability, right? Because you can have ZK proofs or you can have succinct verification. So who thinks that privacy applications are the thing that is dominating blockchains today? Raise your hand. Okay. Who thinks that it's scalability that's dominating blockchain? So for those watching, more people, there's a vast majority in favor of scalability, and I think you got it right. So like more projects, there are a few projects that are really only or mostly about privacy, but more projects are either only about scalability and in fact don't even offer ZK. In spite, as Dan mentioned, in spite of the name ZK attached to everything that is using cryptographic proofs, most of these things, in particular ZK rollups and things like that, and ZK EVM and all these things, when they are implemented, usually like 99% of the time, there's no ZK and no privacy claimed. It's a lot more about scalability. And it's a good question, like why, even though like Zcash was the first instantiation of snarks, and it was about privacy, I think that maybe explains why everyone calls it ZK, but now everyone's veering today towards succinctness. Well, maybe in 5 years it will reverse. Now another good question is, with so much research and so many proof systems out there, why is it that relatively few or variants of a few of them are now in deployment over blockchain? So there are several good answers to that. Well, always taking something from a theoretical construction into something that's more production grade takes time. So maybe, in 5 years' time, if someone does this kind of work, there'll be like, 30 different proof systems, each one of them having 50 blockchain projects using them, maybe. Another thing that is important to understand, and this is something that is relayed across pretty much all projects working in blockchains today with proof systems, is that currently the bottleneck doesn't seem to be the prover. We know that long-term the prover will be the bottleneck, but currently it's not the issue. And another thing that's not the issue is the verification cost of a single proof. That's also not the limiting factor today. So not the proof length, not the gas consumption of verifying. So what are the bottlenecks? So I just want to say that it seems that existing systems are for now good enough for scale. And a lot of the newer systems talk about being better, faster, maybe shorter proofs or more bang for the bit. But these are not the limiting factors today in blockchain. There's another reason tech tends to standardize. If you think about things like TCP/IP, well, it's not the best networking protocol out there, but still it's a standard. If you think about operating systems or programming languages, there are of course a lot of important academic and research works improving them, but when you get down to standards of what everyone uses, there is limited variance there, or limited variety there. And I think it's because the bottlenecks are related to these things that make something usable: productization, developer tools, integration with a lot of other things. Those are, when you look today at the various proof projects and you ask what are they working on and how they're trying to compete with one another, and of course Starkware and its products are part of this competition, it's a lot about developer tools and integration and making things easy and standardize, and for instance EVM compatibility, the ability to use Solidity or other things, integration with blockchains, integration with wallets, with exchanges, with a whole lot of block explorers and those things. That's what seems to be the thing that people are focused on. Okay, so I use a slightly different color for those proof systems that are used in practice. There are I think 6 of them, so Stark Bulletproofs, Halo, Roth 16, and Plonk. And Marley, so maybe, 6 of them, just so you can keep track. But again, there are many, many more. So now I want to talk about I want to give a little bit of an overview of how to think about these proof systems, again, without any math involved, just about, some very broad strokes on how they differ and are similar to one another. I'm just thinking maybe I should pause here for questions. Yeah, I'll pause here for questions. Any questions so far? Yes? So I would say yes and no in the following sense. All non-interactive proof systems are interactive deep inside. Now meaning even when people talk about a snark, non-interactive in the pre-processing model, there is this initial phase of setting up the parameters, okay? And a lot of, even if Fiat Shamir is used in many cases to make things into a snark, into something that is non-interactive, a very good way to think about them in most of the analysis is to basically think about it as an interactive process, and at the very end, if you can, use Fiat Shamir. Now, there's also, I think it's important to reserve the degree of freedom of using interaction, especially over the blockchain, especially if you have an Arthur Merlin protocol, which means that you have public randomness, because practically speaking, we do view the blockchain as a source of public randomness. And for future use, I'm pretty sure that there will be projects that will be using interaction to make things a bit more safer or a bit shorter or so on. I can tell you that within Starkware, we know that if we use interaction, we can reduce the proof size for similar or maybe even better security. And it's a degree of freedom we would like to, it's one of those things in the future to-do list that we would like to use sometime in the future. So if I go back here, I'm pretty sure all of these are I think all of these are going to be, even over here on this stack, I think none of them use interaction, and all of them end up in being a snark. I'm not even sure about that, but it is important to keep this degree of freedom. And definitely when you design systems, like it's better to think of it as an interactive process. Yeah, other questions? Yes?
I think that one of the problems why people don't use it enough is because of the terrible picture that shows of hundreds of options. And if I want to solve a problem, I have no idea which one of these is the one to go. Can you write a flowchart saying if your problem has this property, go here, and if that, go there?
What do you mean by properties?
If the type of problem that you have, it has many parts that are uniform, or I can accept the processing, it can be persisted.
Yeah, I mean.
That would be very useful.
Jumping to the end, the very last slide, I try to convince you that, but of course I'm very biased. I'll say that if you want very short individual proofs, you want to use Groth 16 and frameworks over it. And for any other purpose, you probably want to go with Starks. And there are a lot of choices of programming language above both of them. But that's my biased bottom line. It's of course a bit more complicated still. I think that like in 2-3 years or 5 years, there'll be more of a standardization on which tools are being used by everyone. And so, like, right now, maybe we're in the days where there's SVN and Turtle SVN and GitHub and so on, and maybe in 3 years, there'll be just GitHub, right? No one will use anything else, or almost no one will use. So I think we're still in that stage of like many different things that, yeah.
So currently, what's the fastest system we have? What's the throughput?
What, sorry?
What is the throughput of the fastest system we have?
It's very hard to even compare and answer this because there are many, many settings, but I just want to say, the bottom line, I think, for most of these projects is that the proving is not the bottleneck.
I understand, but I'm thinking about my own system, and I want to ask about, like, say I don't really care about the size of the proof. It can be long for me. Like, how fast can it be?
Do you want zero knowledge, or do you want scalability?
Scalability.
Well, I can tell you that, I'll give you just some numbers that we in our systems in production do today. We, in a single proof, can process the minting of, I think, between 1 and 10 million NFTs. And we do this regularly for, no, inside a proof. Per second, it's even more complicated to answer. But like, okay, let's put it this way. This, let's say 10 million takes us 3 hours. So divide 10 million NFTs by 3 hours. But even this is not a very, we are not optimizing for latency right now. So like, I don't know do you need speed, do you need throughput, do you need so it's very complicated to answer this question. Yes?
I guess could you comment a little more specifically on like, when you say scalability of blockchains, like what does that mean in terms of like, what are the overall goals with these different blockchains you're trying to get using these tools?
Yeah, I think it's my analogy is like a bandwidth for internet or for. So we're starting, right? We all probably remember that there was when we first each of us entered internet, there was a certain bandwidth, and it's been increasing ever since. So that's the way I think of it. Right now, for instance, Ethereum can process roughly 10 transactions, like standard size transactions per second, like ERC20 transfers. And the way I think of it is all of these scalability systems, they're first of all trying to increase the TPS of ERC-like transfers and, by analogy, other more complicated computations. And, then once you reach this new bound, you'll want to do more and more and more. So I can tell you that Starkware says that within StarkNet, our next goal, and this is actually what we're designing, is to reach at least 10x the throughput of Ethereum, meaning we want to reach on StarkNet at least 100 TPS for ERC20 transfers. And, of course, if we end up with more, we'll be very happy, and then you want more and more. So I think of it as there's this capacity that right now is pretty packed, let's say TPS on Ethereum. You increase it 10x, that will get filled, and then you'll want to go another 10x, and this will probably continue for many, many years, unless blockchain is not interesting and everyone leaves. So I hope this answers the other questions. Okay. So, by the way, 30 minutes, ooh, a lot of time. Okay, so now I want to just give a very, okay, maybe I should start by saying anything related to math or science, when you try to survey something with many, many aspects, so it's very hard, right? And you have to pick certain dimensions according to which you're going to describe them. And I'm sure that, so I picked a few things that I think are common themes and differentiating factors, but there are many other ways to parse and review it. Okay. So all of these proof systems have some form of arithmetization, and they have some form of low degreeness. And I want to say a little bit about arithmetization and low degreeness, and then say what are some differentiating factors. So arithmetization, which started with this amazing paper LFKN in 1992, in the early days of proof technology, was this amazing and completely surprising realization that if you want to prove succinctly and then also with zero knowledge statements about computation that are like very generic, like something that doesn't have any algebra in it, any fields or any polynomials, it so happens that if you convert it into the language of low-degree polynomials, suddenly magic happens. And basically, all of my next talk will be about this kind of magic and trying to explain how it works. But let's just pause here. Like everyone who's following snarks and starks and punks, knows that there's a lot of finite fields and polynomials and low-degree polynomials and vanishing polynomials. So let's just pause here and, and acknowledge this ingenious observation from the early 90s that it makes sense to take problems about computation and suddenly convert them into the language of algebra and low-degree polynomials. So here's like a mock example of what arithmetization looks like. You really want to know that the right thing was done when you're not watching. So Bob claims that he knows a preimage of Z. And this is a very, very important problem, right? Practically speaking, you need it in Zcash and Tornado Cash, as Don explained, and in all of the other systems. You need it for privacy, you need it for scalability. So this is all about SHA-256 and bits and moving them around and XORing them and so on. But it turns out that if you do this very weird external construction and convert it via reduction to, let's say, two polynomials. So you started where you want to solve this problem, right? Does Bob, Bob, please convince me that you know a preimage, maybe without revealing any information, or maybe it's succinctly, prove to me that you know a million inputs such that if you sequentially hash them, you'll end up with Z. It turns out that it makes sense to convert it to a different problem that has two polynomials in this mock example, and some degree-bound D, a number, and now ask for a different problem. Bob, you want to convince me that you know a preimage of Z? Well, you know what? I'll be convinced if you show me the existence of, in this case, let's say 4 polynomials, A, B, C, and D, that just so happen to respect this very weird relation. That if I plug them in the right places, so if I replace the variable y with, if I replace the variable y with the polynomial a of x that you supply me, and if I replace the variable t with b evaluated not on x but on x plus 1, and if I take w and replace it with c evaluated not on x but on 2 times x, and this relation holds, then I will be convinced that you know such a z. And this is absolutely mind-blowing. And again, my next lecture will show a few examples of this magic. But why this helps is that it turns out that if there are no such A, B, C, D, or if Bob doesn't know how to find such A, B, C, D, which is exactly the case of soundness or knowledge soundness, then if you now just sample a random x from a large enough domain and just check this relation with A, B, C, and D, and Q and R, you will know with very high probability that something bad is going on. And the reason for that just comes from the fact that polynomials of degree D have at most D zeros. That's it. So if we sample x from a large enough domain, let's say D times 2 to the 128, which just means that we need a field that is of size, bitwise size, 128 bits more than the logarithm of the degree of this, and usually the log of the degree of this is like around 20 to 40. We just need to do one query and everything falls in place. So really a lot of the proof systems can be abstracted away as doing the following thing. You apply reduction, which is arithmetization. Now you ask Bob to commit in some way to the polynomials A, B, C, and D. You do two things. You sample once this relation and see whether it holds, and you also have to enforce low degreeness, which is this second aspect, and turns out to be where all the complexity lies often. So we have a new problem of integrity. How do we know that the right thing was done with polynomials? How do we know that Bob indeed committed to a degree D polynomial? And that's the second magic ingredient that appears in pretty much all constructions, certainly in all constructions used today over blockchain. There are very interesting works in computational complexity that try, of course, to generalize or ask, do we really need polynomials? Can we do it without? Can we do it by other means? And the answer is yes, you can. We don't quite understand what exactly are polynomials required for, but in the context of systems deployed over blockchain, all of them follow this pattern. So now let's talk about, okay, the other aspect is low degreenness that I'll talk about a little bit differently. So okay, if it's all about arithmetization and low degreenness, I want to relate to what Dan said. Why isn't there just one way, which is the best way to arithmetize, the best way to enforce low degreenness, and everyone just converge on that? And of course, it's not that simple. So the differentiating factor between these different systems is the way they arithmetize, and I'll say a few words about that. How they enforce low degreenness, that's maybe the most the most significant differentiating factor. And also, once you go with the low degreenness enforcement method, it entails, or you rely on certain cryptographic assumptions. For instance, do you need a pairing? Do you need a hardness of discrete log and things like that? So that's the third aspect. And these systems differ by what they rely on. So let me just talk from 3 to 2 to 1. So let's start with 3. If we look at these systems, and again, I repeat, this is not a full survey of all the systems out there. Some of them rely on collision-resistant hashing. Some of them require discrete log hardness over elliptic curves, but can use any elliptic curves. They don't need them to be pairing-friendly. They don't need to have low embedding degree. And some of them require pairings and knowledge of exponent assumptions. And there are others that, but they're not used, to the best of my knowledge, over blockchains today that rely on groups of unknown order, so I won't focus too much on them. And the ones that rely only on collision-resistant hashing are, well, assuming that the hash you're using is post-quantum safe, then they turn out to be post-quantum resistant. And they're more in the class of symmetric cryptography. And the ones that are on the right, they rely on number theoretic assumptions, which makes them in particular quantum susceptible, and they rely on what can be characterized as asymmetric cryptography. So that's one differentiating factor. And basically, well, I'm using these sort of medallions to signify where, again, my own subjective and very biased reading is on where things fall. Yes, Huda.
It's the only collision-resistant hash assumption? There's no coding assumptions or something?
There's no what?
Coding assumptions or something?
No, there are no coding assumptions.
You're only assuming collision.
Yes, yeah. Yes.
also
Oh yeah, and all of them. Yeah. Okay. Okay. If you want to make it non-interactive, you're also using. You're also using. You're also using, of course, Fiat-Shamir and the random oracle. But you can instantiate them just with collision resistant if you're willing to do interactive. There are certain optimizations that rely on some unproven coding theoretical assumptions. Yeah, but you can instantiate them and they work perfectly fine with no unproven assumptions, but for the existence of a collision resistance.
What's the delta between with the optimization and without it?
At most 2x. Well, let's at most 2x in proof size and in communication length and verification time. At most. Okay. Well, for some of them, I mean, for many of them, there's none. For instance, I think for Zikebu and Ligero, well, the way they are, okay, they're not used over blockchain, but the way they are, written in the papers, there's no, everything is provable, I think. And when we deploy Starks, we are using this assumption that is related to coding theoretic questions that gives you a 2x saving in the proof length. But if you remove that to the worst possible extent, you will increase the proof length by a factor of 2x, but no more. So it is true that these constructions do rely only on the existence of a collision-resistant hash and do not require any coding theoretic assumption. Okay. So, how do you enforce low degreeness? So some of them rely on various commitment schemes, and we'll talk a lot about polynomial commitment schemes. They're going to be central to the story. And some of them go, well, one branch of them goes a bit further and uses basically hiding specific queries to polynomials. And it's not, well, it also is related to a polynomial commitment scheme, but it requires a little bit more. In particular, it requires this one red branch requires a trusted setup that needs to be done per the circuit. You could make the circuit universal, but then it's per circuit length. Now, what you get for that, and this is beginning of the answer of like, why don't we just have one thing which is best, is that one thing that is very important that you get, especially for this red tree, is you get very, very short proofs in terms of byte count. So famously, the Groth 16 is, I think, either under 200 bytes or, well, certainly under 300 bytes, which is not matched by any of the other constructions. So you get, in this branch, you get the shortest proofs in byte count. Now, I want to talk a little bit about an abstraction of a good way to think about low degreenness. So even though a lot of these systems were not written, the more modern ones, they will talk about how they're constructed from a polynomial commitment scheme. Some of the earlier ones, it was either implicit or even not acknowledged, but like it's all related. You can talk a lot about polynomial commitment schemes, which are a very important cryptographic primitive. So let's just informally define them. So what we really want is a way to know, to allow the prover to commit to a low-degree polynomial of a specified degree. So we want to specify the degree in the field in advance. And then we want to allow the prover to commit, to send some cryptographic commitment to some low-degree polynomial, P. But the main thing is that then we want to tie him to that particular low-degree polynomial, and we would like to query that polynomial at various random locations that the prover does not know in advance and know that the right thing is done even when we're not watching. So we want integrity with respect to the evaluation of polynomials. So this is an informal definition that we'll spend a lot of time on. So the prover sends, it's a protocol, the prover sends a commitment to a polynomial of degree at most d. And then later, you want to allow the verifier to query at any particular z in the field and get an answer, A. And the claim associated with this z, A, and P is that the prover is claiming the degree of P is less than D, and the evaluation of P at point Z equals A. Turns out that if you have this functionality, you have very, very succinct and efficient proof systems. Also zero-knowledge ones, even though in my talks, I'm not going to talk about zero knowledge at all. And then what happens, well, we don't know of an ideal version of this thing where you just get the answer and you know that it was computed with integrity. So usually there's some either proof or interaction, and at the end the verifier decides whether to accept or reject the claim. And what we'd like, as in any good protocol, you want completeness, that there's a way to convince you if you're doing the right thing. You want soundness. If it's not the right thing, then you want rejection with very high probability. The probability is over the protocol or randomness of the setup of this thing. And here are some very nice extra properties that you would like. Sometimes you obtain them, sometimes you don't. So you want knowledge soundness. You want to know that if the prover is able to answer your queries correctly, then in fact the prover knows of a polynomial, meaning there's an extractor that can listen into this protocol and extract from it the polynomial P. You want knowledge soundness. Now efficiency is this generic thing with a lot of variation there. You would like it to have efficient proving time, you would like it to have small communication complexity, verification time, you would like it to work over generic fields, and so on and so forth. I want to highlight succinctness, both because Don asked me, and also a lot of systems give you this. So in many definitions, a PCS will require succinctness, which means that the communication complexity and verification time and proof length are polylogarithmic in the degree, okay? And security, you will also like minimal crypto assumptions, and of course, as in the case of general snarks, you don't have one thing that is just best overall, and maybe someday we will. Okay. So if we go back to these systems, again, this is very, very gross simplification, but you will see, I think, 3 very prominent different PCS schemes or low degreeness methods that are, and these are like classes of methods that are mentioned. So first of all, it's like good to have some mental image. You have Fry that I'll explain in my next talk. You have inner product arguments, and you have KZG. And I think Don is going to talk about KZG more. Okay, good. So we'll cover 2 of them. Don is also an expert on the inner product argument, but I don't know if he's going to talk about that. Okay, good. So I'll talk about Fry. Don is going to talk about KZG, and go read about inner product arguments. They're very, very important and interesting. Here's, again, a very biased and somewhat partial sort of mapping of like pros and cons of various things. So the biggest con of Fry is that it has long proofs, much longer than all the others, in the dozens of kilobytes, roughly speaking. But other than that, it has a lot of good things. So there's succinct verification, succinct setup, transparent, which means no setup, no toxic waste, all randomness coming from the verifier side is just public randomness. You can have them, if you're willing to do interaction, just rely on collision-resistant hashing. Inner product arguments, I think their main problem is just that they require linear time verification, which is, so you have very succinct proofs, which is great, but the very big problem with them is that you have linear time verification. I'll point out that there are many, many techniques related to accumulation and recursion and things like that that overcome this. I'm not talking at all about recursion or accumulation. It's a deep and interesting topic. So there are ways to get succinctness starting from inner product arguments. But if you just take it a one-shot system, that's the main problem with them. But they are transparent. They have short proofs, shorter than Fry, usually in the several kilobytes. And what is very nice about them and KZG is that like once you move to the number theoretic assumptions, you get homomorphic additive properties, which is very important for compressing things, accumulating, and so on. In the Fry world, where you rely only on collision-resistant hash, there's much less additivity, and that causes problems when you want to do things like recursion or accumulation. So both KZG and inner product have additivity. KZG-like systems, their main advantage is that they have extremely short proofs, as I said, hundreds of bytes, and they have the world record in that. They do require a trusted setup. The size of this setup is not succinct. It's linear in the size of the basic computation. And in terms of assumptions, yeah, you need discrete log hardness or knowledge of exponent. So, yes?
In the Fry case, if the collision resistant hash functions that are derived, which are homomorphic, don't need it to be random.
Yeah.
Then what happens after?
It's a terrific question. Then maybe you can start, it's a terrific question. Like maybe you can start doing interesting stuff. I'll just say that often like, okay, so like very long time ago with Professor Alon Rosen, actually in the very early days of Starkware, we looked a little bit about like using lattice-based hash functions with additivity to do stuff. One of the, we didn't reach a conclusion back then, so like I think it's a very interesting area. Part of the problem we faced back then is that usually when you construct a Stark or a Snark or any one of these systems, they work very well as long as you stick with one field. Now a lot of these constructions, at least the ones we looked at 4 years ago, first of all, they couldn't be done over a prime or a finite field. You had to work over like some, Q squared or something. And then it starts to get, but I think this is a terrific direction to look at. Yeah, there's probably something in being able to do accumulation if you have something that is an additive, let's say post-quantum, plausibly post-quantum secure additive hash. It's a very interesting direction. Yes.
What about time of verification in KZG case?
Okay. Roughly speaking, in all of these systems, okay, but for the inner product arguments, the verification time turns out to be so small that even though you could like, usually when these systems compete, and we compete a lot, people don't look that much at it. Why? Because it's it's usually in the 1 to 5 millisecond range for the proof, and that's in a single thread and without optimization. And usually, when you're talking about scale, you're doing it over like huge inputs where it doesn't matter that much. So I would say that both of these give you very small verification time. What is more noticeable and important is since usually the verifier is going to be a smart contract on Ethereum, it's very important to ask about the gas cost of those. And I can tell you that for our proofs for Fry, it's in the millions of gas, whereas a single snark, if it's over the field that is a precompiled in Ethereum, is very low. I think it's around 500,000 or maybe even less, like a few 100,000 gas. But it's a bit of comparing apples to oranges in the sense that here there's no precompile or like specific like subsidy given by Ethereum for these computations, whereas there is for one particular one. If you go outside of that particular one and suppose you have a KZG system over a different prime that isn't part of the precompiles, it will probably be in the many, many millions. So even there, they're a little bit comparable. Yeah.
How easy it is to combine these things together, like say, let's ignore the post-quantum thing, but get, I don't know, the fast properties of phi and together with the short proofs of the KZG, like, by using composition.
Yeah, so it's a terrific question, and I can tell you that a lot of the systems that are deployed on blockchain over Polygon, they are, let's see if I have them like here. Okay, if you go to Hermes and Polygon 0, that's exactly what they do. They get all of their scale from running recursive Starks, but then the very last proof, they use a plonk of that last Stark because they want the 300K verification on Ethereum for that thing. So this is actually being done today. Sorry?
What is the gain?
Sorry?
What is the gain from doing that? From composing the...
Okay, in the end on Ethereum...
But then why not using the KGB to begin with?
Because you get much better scale with Starks, and also you don't need trusted setups, and you can like,
You don't need setup if you use it in the end.
What?
You don't need setup if you use KGG in the end.
Okay. So what you do is, again, what these systems have done, they either rely on one existing... So the nice thing about Plonk is it gives you universal circuits. So there are already a few Plonks that are universal circuits that are small enough, so they have their trusted setups. And now you could apply that trusted setup or that particular circuit for verifying one Stark at the very end. This is what Hermes and Polygon 0 are doing. And then you get all of your scale from basically Stark. The reason you don't want to use the KZG further down is very prosaic reasons. You know, suppose you decided that you have a much bigger computer that can deal with a larger proof size, but like at lower cost. So, okay, now, but you know, maybe in 5 months it will be something else. So now you need to do a trusted setup or, you know, convert everything. Now you need to change it. So like with Stark, you don't have all of that. You basically, okay, this is my machine size. Okay, I'll just go out and do it. Okay. And also I think it just, in terms of the proving time, it does give you better proving time per like, you know, machine construction. Okay, terrific questions. So another question is, what kind of fields can you use? So basically, the ones that rely on number theoretic assumptions, they require number theoretic size type fields and size of fields. And the ones on the left, they can work literally with any field type. So initially, we knew it only for FFT-friendly fields, but now, since our recent work on basically that shows all finite fields can give you things like Frey and Stark with essentially the same asymptotic complexity, you can pick any field. And in particular, if we go back to these systems, most of them, well 2 slides back, most of these systems, regrettably not the Starkware one, work over very small fields, like 32-bit fields, 64-bit fields. The one of Polygon and RISC-0, they go with 32 and 64-bit fields, which I think is amazing, and I told all of these projects that I am green with envy, and I hope we will also move to smaller fields, because they're just much more efficient. So in terms of like, because of these, and to answer Yiftach's question, you get much higher speed also for the, basically the ones related on any type of field and collision resistance.
Is there security, like working with smaller fields? Like
No problems. Well, I mean,
they use eventually a low degree, use many points or something like this, or?
well, at some point you need to do either some sort of sequential repetition, or you need to move to an extension field in very particular areas, but the whole arithmetization and a lot of the work and the low degree extensions can all be carried out over small fields. And yeah, so at some point you do need to involve, you know, if you work with a 32-bit field, at some point you need to take the degree 4 extension of it, but it's, okay. Yes?
Are there any proof systems that are similar like this that work over rings?
No, and it's a terrific question. I think in my next talk there's actually a question, not that I know of. I mean, Dan, do you know of proof systems over rings? So, okay, ask Dan, there are. But I'm not aware of, yes?
No, it's just SQL.
Another aspect, again, so answering just the question of why isn't there just one, and yeah, it is a mess. Some of them are scalable. The definition that I use for scalable means that you have 2 things happening at the same time: quasi-linear proof generation and polylogarithmic verification. And semi-scalable, again, I'm just making up this definition, is something that after a one-time linear pre-processing, you now have quasi-linear proving time and polylogarithmic verification. Transparent means no trusted setup, only public randomness, or Arthur Merlin. These are all names for the same thing. And again, in terms of scalability, well, like true scalability, which means succinct setup, all of them, but for the knowledge of exponent-based ones give you that. And this again answers a bit Yiftach's question on why not use KZG or this line all the way down. I think that's a bit of an explanation. Yes?
Post-quantum, from applications, how often you find applications that post-quantum is really important?
Today over blockchain? I would say never, right now. And why? Because a lot of the signature schemes and everything else is like quantum susceptible.
The question of if you can revert this 30 years from now, you know, whether that will be an issue.
I'll defer to Dan on, no, like...
But I would guess that most applications don't.
Yeah,
It's interesting that privacy is unconditional.
Right, but yeah, I'm focusing just on now on like mostly on scalability. So, and about the apps, I don't know. Yeah, probably you can break a lot of things, like if the signature is, well, I don't know, can you? Like if you broke RSA, will you also learn what the, like in 30 years? Okay.
Yeah, it depends on how you use it.
How much time do I have? Should I? What? Great. So future proofing is also important. You know, how quantum susceptible or how long the assumptions have been around. Let me just go very quickly and say, again, it's a very biased view, but I think it's also starting to pan out in, you know, what systems are being used. A lot of them, like, first of all, there was only basically Groth 16, so all systems deployed on it, but you see that some of them are moving more and more towards the Stark area, even if not fully, at least in most of the aspects. So I think, but again, I'm very biased. I have a particular, fond place for these kinds of proof systems. And I should say, I'll say why. They have I think they have the most reliance on like very old and beautiful math that is quite deep, but for me, first of all, I like that. Maybe it's also safer, who knows, but just I like that. I like more math and like less assumptions. So I think that for short proofs, definitely you want to use Groth 16 snarks. Nothing comes close to that. I think that for everything else, you're better off with Starks. And that's the end. Thanks.